Okay, hello everyone. Welcome to another discussion session on TIFR problem solving. So this problem came in 2019. So we are now currently pursuing the 2019 question paper, question by question. So this is a problem that requires three things uh, to understand what transposition of matrix and the multiplication, how it goes. Secondly, what are ranks, and lastly ranks and rank nullity theorem, and lastly a very simple theorem in inner product spaces. So if you know these three things, it is pretty much easier to uh, understand how to proceed with the solution. So let us go to the solution. So firstly we will address the second part of this question, that is, if A has complex entries, then it has necessarily K, A into A transpositions. So the fact is that it's not true, quite obviously. I mean, just take this matrix 1i 0 0. Just take this A. So this A is in M2C, and if you take the transposition, so then A into A transposition, it will be 1i 0 0 1i 0 0. Okay, so if you take the product, then it's 0. It's the 0 matrix. But individually, both these, individually the matrix E has rank 1. So rank of A is 1, but rank of A transpose is 0. So we give an example of matrix whose rank is 1, but A into A transposition is 0. So thus it's quite obvious that the second option is false. Okay, so both E and D from here gets automatically eliminated. So it's between B and C. So for that, we will require this. So rank of A is always equals to rank of A transposition. Okay, because row rank is always equals to a column rank. This is the reason that rank of A is always equals to the transposition of that same matrix. So what we get from here is something. So let's say let X be a vector such that E transpose of X is equals to 0. So I'm taking a vector from the null space of A transpose. Okay. So what I'm doing, I'm taking the null space of A transpose. So what is the null space of A transpose? This is the collection of all X in n cross 1. So belongs to n cross 1. So you can actually write it like this. So for now, I'm taking it all real because the complex part is already taken care of. So let's just take Rn such that A transpose of X is 0. Okay, so this is what I'm taking as the null space. So now, if I have A transpose of X is 0, from here, what do I have? So from here, I have this. Now the inner product structure will come into the picture. So I have A transpose of X comma X. This is also 0. Inner product spaces. Just the very basics, nothing too much. So because this is always 0, so the inner product is 0. It's not a big deal. Now This is the property. This actually implies, this is one of the properties of inner product space, that this is this. Okay. So the moment you have this, that means the norm of A to A transpose X is 0. So this will actually imply that A transpose X is 0. So we already know that if A transpose X is 0, then A into A transpose X has to be 0. So one-way containment was always there. So null space of A transpose is always contained as a subspace of null space of A transpose. But here what we have done is, if we take any vector from the null space of A transpose that belongs to the null space of A transpose itself, that means the nullity, so that means this gives the reverse inequality as well. So the nullity of A transpose is same as the nullity of A transpose. So which implies that rank of A transpose is equals to rank of A transpose, which in turn implies rank of A. So this is the very basic rank nullity theorem that we have used here. Okay, so the three things that we have used here: first, first we eliminated this option 2. That was the first. Indeed, if it has real entries, then A transpose has necessarily rank K. So thus 1 is true and 2 is false. So 2 would have been true. So the option 2 would have been true if we had this, that a conjugate transpose. So if we had tackled it like this, then by the same inner product argument here, we could have concluded that it is also true for complex entries as well. So one of the remarks that you should take from this problem is that E transpose has same rank as A. So this is one of the remarks that you can actually conclude from this problem. So thank you for joining us. We will meet again with another problem next time. Thank you.